will be actually two talks about recent research. The talks that we have are not always research, and they're not always recent, but they're always interesting.
So today we're going to deal with Dr. Griffioen.
Will tell us about what to do with an SDN switch.
All right. Is this needed for recording purposes, or
Yeah, that sounds cool.
can I wander around? Okay. All right. So yes. So let me tell you. I'm going to tell you a little bit about some of the projects that we've been, a particular project that we've been doing here in Laboratory for Advanced Networking regarding software-defined networking, and the goal of this is actually going to try to enable some high-performance science flows across our campus. So it actually is in conjunction with some high-performance computing research that we've done as well. I'm giving this talk, and in fact, this is sort of a follow-on or shortened version of the talk I gave earlier at one of the GENI conferences. So if you want to go find a more detailed version, I can point you to that as well. All right. So I should also, first of all, mention the people that are actually doing the real work here. And so if you have any technical questions here, these are the people that know the detailed answers. And I'm going to give a high-level description of the problem that we're solving, and I'm going to use a lot of hand-waving sort of at the solution, in part because of the time limitations, but trying to give you an overview of the particular problem that we're solving. So if you, basic format of my talk will tell you a little bit about our problem and the current solutions that people have provided out there and used, and then I'll tell you a little bit about our approach and some of the solutions that we've used, as well as a demo. All right, so if you look at, and this is really, I'm having a difficulty here. These are not showing up on my laptop at all. So, does someone know how to make the window bigger on your display, your slides here?
Is it a Mac?
Yeah, you don't know.
I don't know.
Well, we'll just move forward. All right, so the problem is that many university researchers now across campuses are dealing with very large data sets. And these are often on the order of gigabytes, in several cases terabytes of data. And they're often moving these massive data sets around. They have to share them with other researchers. So the question is, how do we actually deal with this from a networking perspective? So not only are they becoming prevalent, but we have to somehow deal with these on a regular basis. And we need to have networking support built into the campus networks that are going to enable this type of transmission. So the question is just, well, are we well designed for this? If you look at the standard network design, it looks something like this. You often have a series of buildings. Each of those buildings has a network access into the campus core, so there's a link bringing you to the campus core. And within the building, there's a whole series of switches, often arranged in sort of a tree structure. And they then end up talking to your computers at the lowest level. And then once you're at the campus core, you now start working your way toward the internet. And on your way out toward the internet, you're often going through what we call a series of middle boxes. You may also hit firewalls, and ultimately you hit your campus edge router, and that leads you into the internet. This is true for most buildings, and in fact, even if you have a high-performance computing center, like our Center for Computational Sciences, the high-performance computers are also going to be usually connected behind this particular model. So when traffic is flowing, it's typically going to go out over the campus core through this series of middle boxes, and much of our campus information now is going to what we call north-south. That is, it's headed from end systems here out into the internet to cloud services. So in many cases, you may be seeing people move large data sets. All right, so the problem here is that middle boxes are performance limiting in the sense that they are often doing some sort of deep packet inspection. That is, they're looking inside the packets to determine whether or not these packets have viruses. Are they an allowable packet? Are they going through some port that we don't want to allow? It may be that we actually just want to rate limit it, or they watch somebody's watching a high definition video that we may want to rate limit. So there's a variety of different middle boxes out there. They're very important to campus networks for security and stability purposes, and as a result, we want those there. We actually want them to enforce our campus policies at the edge of the network. The problem is that these boxes pose a bottleneck to performance. So if I'm actually moving data in and out of the campus network, and I want to move it at extremely high speeds, I'm moving terabytes or at least gigabytes of data, I, in fact, would like to avoid these boxes if at all possible, because they're going to slow down my connections. The other thing is that you actually find these boxes within the campus itself. So in front of buildings, we may have particular firewalls or other sorts of middle boxes that are doing some sort of deep packet inspection. You often find them in front of various centers where we have particular policies that we need to enforce.
Jim?
Yeah.
But isn't it the case, I remember you talking about this natty, so isn't it the case though, if you were on, say, your phone, you have to go through one of those?
Yes. So if you are on our wireless network, for example, you get an address that's not actually an address that's accessible in the outside network, you have to go through a NAT box. Right, so that's another example of a middle box. All right, so going back to our example here, if you've got a traffic that's flowing that direction, the question is, how do I solve it? And the conventional way that's been pushed out there in terms of how you solve this is to take your high-performance computing resources, things that are going to be doing lots of huge data transfers. So let's say you've got a supercomputer that we want to move data in and out of, and we may want to move data from the supercomputer locally to our supercomputer at one of the national research labs. So what we do is we take that supercomputer and basically essentially move it to the edge of the network, outside the firewalls and middleboxes, and we essentially create what's called a science DMZ, science demilitarized zone, where outside the firewall now, you are not going through the middleboxes anymore. You have a direct shot into the internet, and as a result, you can end up with extremely high-speed transfers. So what we often would see on our campus here, our transfer rates in megabits, hundreds of megabits per second. If you were going out from one of the buildings, if you went straight out from the campus edge, you can actually get into the gigabit per second range. All right, so this works very nicely. The problem is that, so the basic idea is that you move your high-performance computing system to the edge, and as a result, the advantage is that your traffic that you're moving between your high-performance computing resources and national labs, for example, bypass these middle boxes and get much better performance. So this has been a solution that's been employed by campuses all across the country. And the problem, though, is that by doing this, these machines now are outside your firewalls. They're outside the middle boxes. They lose the protection capabilities that you had if you were inside of them. So obviously, only the campus machines are protected. They're the machines outside there become less protected. Now, there are ways that you can try to protect it, but the purpose of putting it out there is actually so that you aren't going through those boxes. As a result, you can't apply policy. So, for example, if I move a box outside there and someone starts watching Netflix or whatever, they can do that at very high definition because they're outside that. So the entire machine has moved out, not individual flows, for example. And the third thing you have here is that you have to sort of, as a researcher, decide, do I want my machine to be connected to the science DMZ or do I want to be connected to the campus network? And I have to make a decision there as to where I'd like that to be. And once you're there, then you're going to have whatever characteristics are associated with that. Okay, so you have to make that decision of moving. All right, so how do we solve this problem? Before I do that, I need to give just a little brief definition for any of those of you who aren't familiar with software-defined networking, which is a new area within computer networking that actually is looking at programming the network itself. So SDN refers to software-defined networking, and the basic idea is that you can run software, and software will now define and determine how switches and routers in the network behave. In particular, it's going to modify the forwarding tables, so the way packets are going to be forwarded by routers. A very popular protocol for doing that is called OpenFlow, and this is a way of talking to switches and routers to configure their routing tables, their forwarding tables, to control the way packets are moving through the network. We actually talked about a OpenFlow controller. It's the piece of software that actually runs and controls your your switches inside of your network. So the idea is that you would run a piece of software on a PC, it talks to your switches and routers, and tells them what to do. Now, the typical routing table looks something like this. This is just an example, where when packets come into a router or switch, there's a forwarding table there. And it looks up and says, where is this packet destined for? And so if you look and it says the packet is destined for a particular address, and usually this is specified as an IP address range, then you say I may send it out port 8 on the switch, for example. Or if it's a different address range, I might send it out port 2. Or if it doesn't match any of those, then I might send it out default port 5. So this is a sort of typical forwarding table type structure in a switch. What SDN does is it allows you to actually talk to the switch and insert rules into that table using software rather than having the router itself set up those rules. So in this case, you can actually talk to a switch and you can say, I would like to match packets that match a particular rule. In this case, for example, I might say, if they match the address 128.163.10.12, okay, then in that case, I would like you to send them, and with a destination of 128.163.140 in that range, that subnet range, anything matching the last 8 bits there. And if it's destination to port 22, the SSH port, then I'd like you to send it out to port 8. So you can first see that we can first of all match against many more fields in the packet. And once we match that packet, then we can say where we'd like to send it. Another thing that you can do is not only can you match multiple fields, once you've done that, you might say, okay, I matched this packet here. I'd actually like you to rewrite one of the fields in the packet before you send it out. So you may say, it came in, this is the packet that came in, it was destined to a web address, maybe it was coming from the exact same machine here, but now destined for a web address, and we would like to send it to the secure port there. So we rewrite it from port 80 to port 43, for example. And then we send it out to port 3. So by talking to switches and routers, I can actually tell which packets are coming in, what they're matched against, and where they should be sent out. All right. So having said that, yeah, go ahead, Gene.
So does it add an extra point of vulnerability though? The fact that those forwarding tables exist, is that maybe sort of a new thing that people hack?
Yes, so there is the potential, the concern here is that since software is interacting with those switches, someone could potentially attack those switches and control the switches. Yes, that is an area of concern, and there are various ways that they try to do that. One is that the control channel is usually required to be on a separate VLAN that is only for control purposes. That's one of the ways. Okay. What we've been doing is to say, well, maybe we can use this technology to actually implement what we call an all-campus Science DMZ. And the basic idea is this. Basically what Science DMZ has been doing is saying, I'm going to take some of the traffic on our campus and we're going to allow it to bypass these middle boxes. Maybe we could do this rather than physically moving the boxes from where they are to a Science DMZ. We can in fact actually use SDN to pick up individual flows off of a box and say we're going to route them around the middle boxes and send them straight out toward the edge. All right, so our idea here is to, first of all, use SDN routers on campus. So you have to first replace all your routers with SDN-capable routers. The next thing you need to do is create a middle box-free path from endpoints to the edge so that it is possible for us to have two paths, one that goes out the normal network and one that goes out the other way. Then we're going to write rules and configure them so that we can potentially forward that way and dynamically insert them. So let me just try to illustrate this quickly to bring the point home. Here's our standard network. The idea is we should insert software-defined network switches in our network, and you may put them all through a building, or at least at the head end of a building, where I can intercept packets that are leaving, headed out towards the campus core. Once I do that, I also need to build out a secondary path that will bring us out to the edge router without going through the middle boxes. So we define that, we call that an SDN core, so that now at the SDN switch I have a choice whether I can either go through the campus core or whether I can go through the SDN core. Then we need to write software And this is really the heart of our VIP Lanes project, to write all this software. And today I'm not going to get into the details of that software, given the time limits. But the idea here is that this software would actually control these switches, insert the right rules there that are going to match packets. Based on which packets match, it will decide which direction they go, whether they go into the campus core or whether they go into the SDN core. So if they match our standard, oh, yeah, go ahead.
How does the SDN switch confirm that if it's looking for a certain IP address, how does it confirm that that's actually the science entity, not someone who's just trying to get because normally routers use MAC addresses to determine which computers, which on the network. If you could find out the MAC address of the HPC, you could pretend to be it maybe and trick the SDN into giving you the high-speed traffic.
Okay. So there's let me let's make sure I get your question correct. Are you worried about people spoofing and trying to say that I would like my traffic to go out the SDN network?
Yes.
Okay, are you trying to steal traffic?
Yeah, is that possible? Or is that useful or?
Okay, so the way I've described it here, the forwarding table is simply going to look into a packet match based on the fields in the packet. If someone has spoofed those fields, or was able to spoof those fields, it would match, in which case the rule would be invoked and it would send it out that direction. Okay? So in that sense, we're not solving any of those particular problems.
Okay.
Okay? There are ways to address those, but the basic format of the SDN is to do packet matching, and then there's an action and forwarding.
Okay. So it's not a concern if someone matches those packets and then uses Netflix on your private computer.
That is a concern that people spoof things. The reality is that there are other ways to handle that.
Okay.
So there's other things in place. And when I said there was a tree structure down here, that doesn't mean that these switches aren't still doing a lot of what they used to do, or that there might other be software that's doing checking to make sure that packets that are coming from a particular range are in fact from that actual range. Okay. So by default, packets are going to head through the core. And if we actually insert a set of rules over top of them that have higher priority, and these rules say, I'd like to pick off a packet, we can actually pick off certain flows and then send them out our SDN core. And the idea there is that we'd actually get much higher speeds. The advantage now is that we can actually be sitting at a machine, and you could be watching Netflix, and it could be going out through our standard campus core because it's not a privileged flow. It would be rate limited using our middle boxes to make sure you're abiding by campus policies. But at the same time, you could be doing an SCP to Oak Ridge National Labs with a scientific data set that has been approved for high-speed bypass traffic and going out at multiple gigabits per second. All right. So ultimately, you can now think of our entire campus as being a high-performance science DMZ without the need to actually create a science DMZ. All right, so what does this involve? Well, this involves actually two things. First of all, we need to have routers in the network that are capable of doing standard forwarding. So they have to play with the network protocols much like they always did. So you need to be able to exchange routes using whatever routing protocol, whether that be OSPF, whether it be BGP, whatever it is, it needs to still be able to do that. And by default, it should be routing packets that direction. The other thing then that we need to do is create control software to be able to understand what the topology is and be able to define routes across our SDN network that will bypass the middle boxes. So we need to know which are the middle boxes. We need to bypass them. We need to also be able to accept, the software has to be accept requests that say, I'd like to turn on what we call a VIP lanes flow. And once that's been requested, we now need to compute the path from the requester's machine to the edge of the network. And along that way, we have to actually rewrite rules or place rules into the table that are going to say, match this particular packet. If I see that, forward it out another particular forward on that. Then, obviously, we need to make sure that the rules are there for the duration of the flow. We have to remove them at some point. We need to make sure that if there are failures, that we can handle that. You don't want a flow to a router to suddenly go down. and disrupt the flow. So we need to be able to handle those things as well. So the VIP link software does a lot of this, and I'm not going to be able to go into the details of how it does that. So we've actually added several features to this. One is that we have config files that we have used currently to identify what are middle boxes. Ideally, we'd like to be able to discover this dynamically. It's currently difficult, but we use config files for that. We've written a VIP link server that actually does authentication to verify who you are and that you have privilege to turn on or turn off a VIP links flow. We've written a path computation service that actually computes the path from your machine through the campus backbone network, bypassing the middle boxes, and potentially, if you need to go through services that you may in fact still want to have in your network. And then we've also added new modules into a controller, an open flow controller, that allows you to insert rules and to actually extract monitoring information as well. So there's a variety of different pieces that we've added into our system. All right, so going back to our example, let me just sort of give you an example of where these kind of things become a little bit tricky. So here's an example where I may want to transfer data, in this case not north-south, but actually east-west between two machines. So here's an example where the path that you normally take would go through building A, it would then jump to the campus core, and from the campus core come back down into building C. Now the campus core is a routed network. That means that the building A is typically on a different subnet than building C. And as a result, there's a router inside of the campus core that the packets are going to go through. What that means is that typically what would happen is when you're going to send from this machine's going to look it up and say, how do I get to the machine over in building C? And it's going to say, I need to send it to a router located in the campus core as my first hop to get there. So it addresses the packet to the campus core. Once it gets to the router there, that router picks up and says, I need to forward it on to the machine in building C. And it changes the packet, modifies it, and sends it on to building C. At this point, this machine over here will receive a packet that came from a router up in the core. That's what it's expecting. Now, we can come along and say, you know what, we have an SDN path that's much better, much faster, and much higher speed. Because these are newer routers, they're higher speed links. I can actually take a path now that goes up to the SDN switch, hits the SDN core, shoots it back down to the SDN switch in building C, and goes straight to the router, which is the destination. The problem now is that I can insert rules along there that says forwarded, match this packet forwarded, match this packet forwarded, match this packet forwarded. What will happen then is that ultimately, at the building over there, where building C, you will end up with a packet that came directly from the host in building A, and it's expecting a packet that came from the campus core router. So one of our things our path service needs to do is needs to look at this and say, you know what, it would have expected a packet to arrive from a router on campus. We actually have to rewrite the packet right before it gets to the destination to make it look like it came from the router on campus, otherwise it may in fact reject it. So these are some of the problems that the software is dealing with and actually has to do in terms of computing the paths that it's taking across campus. All right. Another nice thing you can do, which I didn't show in the table example there, is you can actually not only say rewrite a packet, but you can just say count them. I can say count the number of packets that went through and keep a counter there. So one of the things that we've been able to do is to actually go into our routers on campus and say, I'd like you to put in a counter for this particular flow between these two machines and keep track of how much traffic's going back and forth between them. The standard routers will typically tell you how many packets went over a particular port coming off the router. They won't look at the particular individual flows, or at least not in real time. So this allows us to get an actual real-time graph. In this case, this graph that I'm showing here is actually showing you different plots. Each one of those plots is a different switch along the path, telling us what that particular count is of how many packets have gone through at that switch. So if I have, in this case, 1, 2, 3, 4, 5, 6, 7 switches along the path, I get 7 different counters. And you would expect them to be identical, The reality is that because you're probing these routers, saying what's your packet count currently, you'll find that they differ slightly. It may be that at the first router I've had 10 packets, the next one we've only seen 9, maybe the next one we've only seen 8 at that point in time. So you'll see that these bounce around a little bit. But in reality, the idea is that you're getting roughly the same performance. All right, so this gives us very specific flow, specific monitoring capabilities. All right, to test this, we've actually done a couple things. One, first thing we've done is to actually implement this using a GENI topology. GENI allows you to create testbed networks using virtual machines arranged into whatever topology you would like. And we spent some time creating a relatively complex topology. And this sort of depicts the topology that we created in GENI with different nodes acting in different ways. So we have a whole bunch of nodes here that act as end hosts. We have basic switches that are performing sort of layer 2 switching. We then have distribution nodes, much like our campus network has them. That would then route to a core network that's doing layer 3 routing. We also put in an SDN switch into our simulated network, and we have a couple middle boxes at various locations inside the network. And ultimately, we head out through the UK router, and for purposes of rewriting addresses on the way out so that they come back in through the SDN network, we add a NAT box in there as well. All right, so this is the topology that we've created to do some initial testing. And I'll quickly show you sort of a video demo of this. And so here's the example that I showed you before, where I have a node over in building A, sending to over in building C, going through the core there. And these consist of slower boxes. In fact, you node over there is going through a rate-limiting middle box that slows us down to around 10 megabits per second. At that point, once we've started this flow, we will actually go in and run a script that will compute, we'll say, I want to go from here to there using a VIP lanes path, and it will dynamically compute the path, realize that, oh, I need to do packet rewriting. We'll send it through the SDN switch up above, and as a result, we'll actually end up running at much higher speeds. All right, so let me see if I can demonstrate this. All right, so on the bottom here, we're monitoring all the switches along the path that's the default path. And on the right-hand side, we will eventually be monitoring all the switches that are on the high-speed path. And so this is just getting the monitoring going. This is setting up the counters and pushing rules out there to do counting in all of those particular switches along the way. The next thing that we're going to do here is start up a server on the C machine there to accept packets, and then we're going to start up a hyper system on the client that's sending packets. And what you can see here is that it starts out initially, and it's getting about 9 or 10 megabits per second, which is just exactly what we were sort of expecting. So let me stop it there. And looking at the packet counts here, they're coming through at about 1,800 packets per second that we're seeing. And it's roughly the same, but we're seeing slightly different numbers at the routers along those paths. The next thing we'll do over in the window over there is to actually go and say, I would like a VIP lanes path between this host in building A and the machine in building B. At that point, the software will go out and compute the path, figure out what the rules are, and automatically insert them in. And at that point, we should actually start to see traffic switch, which would mean the traffic over here goes to 0, the traffic over here actually should come to life, and you should start to see it coming through at higher speeds. Let's start this back up. All right, so at this point, we run the script over here. It says I want a VIP lanes. You should see the traffic here start to drop, and it should start to pick up over here. And you'll note that it jumps to about 10,000 packets per second, and you'll see the rate up here jump to about 100 megabits per second. So this sort of demonstrates how we can just dynamically pick up a particular flow and send this traffic in that direction. All right, so that concludes my talk. I see Rafi standing up, so